Hi. Okay, so this is the video for assignment number 3 of econ0010. It is currently midnight because I have a really good sleep schedule. God, I want to go to bed, as you can see there. But we're going to be going over questions 5, 6, and 12 in this one. So, first of all, let's start with 5, okay? So first of all, we've got to state Roy's identity. As I've sort of indicated here, of course, as usual, my worksheets are going to be posted in the description in case any of you guys need them. But we've got Roy's identity here, which is xi, where each I is an individual item, or more of like a good. And you've got the thing is the demand function is going to be the partial derivative of the indirect utility function with respect to the good, the price of the good, and divided by the partial derivative of the utility function with respect to m. So this is gained from essentially dividing the finding that you can see later, that the partial derivative of v with respect to the good is, wait, I've done that one wrong, hold on. There we go, good thing I'm checking. Is equal to negative lambda over xi, and then if we divide by that lambda on each side, we get this equation, and switching around the negatives, you get the Roy's identity. Obviously, it doesn't ask you to explain every part of it, but I just thought if I have to make it intuitive, I will. This is explained also in the book a bit further. Now, to use Roy's identity here, let's just try using it for x1 in this case. Okay, so x1 is going to be using the price one, right? So first of all, you can see here that we've got the partial derivative of the indirect utility function. And what we've done here is we've essentially just partially derived relative to P1. So you can sort of see here the power is reduced, and we're just moving alpha to the front. This is very simple stuff. We can see the partial derivative of the indirect utility function relative to m here, because it's only 1m, we just simplify it down to 1, and then we essentially just get this simple function here. Now, using the identity, we divide these two, making sure to minus the first one, which gives us this big expression over here, cancelling out the P2 and P3 here, because they're the same on each side, and then simplifying down P1, we get alpha m over P1, which is equal to x1. So you can see here we've got the demand function, which is x1 is equal to alpha m over P1. This method can be repeated for all the goods here. Given that they are all in the same situation, relatively, you do not need to do a unique process for each of these because they are all essentially the same process. So all the demand functions are going to be about the same. So you're going to have beta m over P2, and you're going to have gamma m over P3 for x2 and x3, respectively. That's what I at least got. Of course, disclaimer, everyone again, I don't know everything. I don't know if it's right, okay? But just this is what I got, okay? So this is the demand functions that I got. For 6, we're going to use the integrating factor method. At least that's what I did. So you can see here in the question that we've got dy dt. Okay, so it's all separated out. And we've got 1 over 2t times by y. Okay, so we regard 1 over 2t as the function that we're going to use for the integrating factor. So as you can see here, I've done e to the power of the integral of that function. So this is normally what you get. You normally have the function there, the function that's being times by the y, and you integrate that function and put it to the power of e. So you can see here that I've done that. I get e to the power of half of ln t. This moving that into the natural log via log rules, you get ln is ln of 1 over root of t, and because you've got e and ln in there, you can just cancel those out, and you get 1 over root t. Multiplying the entire differential equation by this, you get this equation here. and which we can notice that it is equivalent to the derivative of this function here. So it's sort of like bringing them together. This is sort of like factorizing these two up, more or less. Then, in order to perform the inverse and find everything in terms of just, remove the derivative out of it, we integrate both sides. So you get y over root t, which is equal to the integral of 3 root t dt. This gives you y over root t is equal to 2t root t. At least I think it is. Which I think I got that, yeah. One moment, let me check that. Nope, I was right. I do know what I'm talking about. Kind of weird how I went back on that. Anyway, we got that there. And so if we multiply by root t on both sides, we then end up with the general equation. Obviously, we have to remember to add the c on the integral, otherwise we only have a very specific equation. So this is the general equation I got. The question also asks you to describe the behavior of the general solution when t is small and positive. We use the small increments formula for this. So the small increments formula is stated somewhere in the book. I think you could just look it up in the index and it'll be there. But it also states that a small difference in a change in the function is comparable, or at least approximate, for that small change times the derivative. Okay, so for any small change, we're going to essentially experience approximately the same change if we times the entire function by the change itself. So we get the derivative of our general solution, which is found to be 4t plus c over 2 root t. And then we know here that it's timesing by h. So for a change that's in t that is sufficiently small, we can say that the general solution changes by about 4th plus ch over 2 root t. That's about this small enough change. Not entirely sure if that's right. In fact, I think it might not be. I'm not entirely sure, but that's what I did. Again, don't take my advice as granted. This is just what I did. I'm pretty sure the integrating factor method is correct, but I'm not entirely sure about this last bit. So if you probably look at my document and probably editing it, okay, I might have a different thing. Who knows? But that's what I've got right now. Right, for number 12. Number 12 was the first one I did because I just liked it. It was easy. So for any optimization of a utility function, we need to find points where the budget constraint is tangential to the utility function. This is what you guys should know at this point. So for 300, we can quite easily see we've got the constraint here. 4x1 plus x2 equals 300. And so we're going to essentially find the derivative of that budget constraint. It's -4, as we know, so that's our MRT. And now to find the function for the MRS, we implicitly derive our utility function, which gives us a derivative of -20 over root x1. Matching these two derivatives up, you get a value of x1 that is optimal, which is 25 in this case. So then we plug that 25 back into the budget constraint, and we will get a value of x2 instead, which is going to be 200. So the best combination for m equals 300 is x1 equals 25 and x2 equals 200. That's what I found. The second part here is a little trickier for A. For M, essentially it's the same process as what we were doing. It's the same utility function, and the derivative of the budget constraint is unaffected by 50 or 300 or 10,000. So we'd go through the same process, and we'd get the same value of x1. But the problem is, we would then get a negative value of x2 if we subbed in that value. So it's almost like you have a possible value, but it's negative. If I show you guys what I mean here, let me just show you. So you can see here, I've got a graph open. This is a piece of software I commonly use. It's called GeoGebra. So I use it for a lot of my graphing. It's quite useful. It doesn't have many sophisticated tools, but it's good enough just to show you. straight up. So I'm just going to show you guys what the budget constraint is generally. So we've got this here. Okay. And then what does it say here? What did I do? Yeah. So we've got a utility function here. And if we were to plug this into the utility function, we would see, well, yeah, you'd have negative 50 and you'd have positive 25. So you'd have 40 multiplied by 5 minus 50. Is that correct? Yeah. So 150 for the utility function, I suppose. Plus y. Did that work? Did it work? Did it? We've been touching. What's happening? I swear I had a better representation of this earlier. Hold on, give me a moment here. I'm just trying to decode what I've written for myself. Yeah, so we'd have an optimal value of negative 25 and negative 50. So 150 is equal to that. Yeah, it should be that. But anyway, regardless of that was a useless detour. You can't have a negative value of y. Okay, so because we can't have an optimal value necessarily allowed by this, we're going to have to pick a budget, a point of the budget constraint that's at a border, so a boundary condition rather. So we're going to basically say, like, okay, what are the boundary conditions for the budget constraint, and which one's better? So the boundary conditions for our budget constraint, which is 4x1 plus x2 equals 50, is 12.50 and 0.50, and we get a utility of 14.142 and utility of 50, respectively. So we would say that the border condition that works for us best is going to be the one where we are maximizing x2. So that's generally what works for us. Okay, and we would use, in this case, just 50 for that. It would just be 50. So, I don't know. I'm just trying everything. It's all very fun. 50, and then we would do 50 is equal to 4 root x plus y. And it would intersect the same point, I believe. Yeah, you can sort of see up there. So you got the same point intersecting there. If this worked, what the... Now, what have I done wrong here? It's intersecting 146. What? What? Fuck it. Okay, alright. 0. I put 0, didn't I? Clearly I have done something wrong. One moment. My apologies, I was stupid. It's supposed to be 40 root x1, not 4. Of course I got it wrong. It's all good. Anyway, that hits the boundary condition fine. So that's done. Hooray. Dear Lord. Not too happy with myself for that. Anyway, moving on. So, now we have a minimization problem. Should be fairly easy. So I've used Lagrangian here. So we're minimizing first with a equals 4 in our constraint. We see this just 4 at the end. So we're using the regular Lagrangian method. I'm coming up with first order conditions here. I believe first order condition. Something. It's something at the very least. So we're setting the derivatives as 0. We get values of x, which is lambda plus 1, and y, which is lambda of 2 plus 1. Plugging those into our constraint, we get the value of lambda must be smaller than or equal to 2 over 5. and then rearrange and then plugging in our values of x1 and x and y into our function we intend to minimize, we find that the lambda here shows that the value of the function is going to be determined by lambda squared plus lambda squared over 4. Now, how do we minimize this? Well, as a matter of fact, because lambda can be smaller than 2 over 5 and every one of these values is squared, we would be better off minimizing lambda close to 0, because this is essentially going to almost be like an absolute value, right? Because if we're squaring, we're going to have a positive value either way. So we probably want to make our value as small as possible. And here, given that lambda can be smaller than 2 over 5, we can essentially set lambda to 0, and we have minimized it. So that's essentially the best solution for us. Now, the other one is a little different, because we get a different constraint for lambda. So we go through the regular motions, and then you eventually get to a budget constraint, which is lambda must be smaller than negative 2 over 5. Now, we do not have the option of making it 0, so we have to find a value that is equal to or less than 2 over 5, which minimizes it. As the same thing is true, we want the smallest value, because if you're maximizing an absolute function, okay, then you want to pick a maximum value for that. But if you're minimizing that absolute function, you want to pick the smallest value that is in absolute terms. And in this case, it's going to be negative 2 over 5. Okay. To give you guys a bit more of a innate understanding of how this works, let me bring up GeoGebra again. Here it is again. Okay. So let me just show this. Yeah, so we have x minus 1 squared and, yeah, plus y minus 1 squared. And this is going to be equal to, what were we saying it was equal to? Yeah, so it's yeah, of course. Actually, yeah, let me show this a little. Yeah, just give me a moment. Let me type in all my numbers, and then I'll show you guys. All right, I've got it modeled for you. So this is the intuition for the first part. Okay, so most people probably think 2/5. Okay, so see here we have a slider for lambda. Okay, lambda is starting at 2/5. Okay, and it can go lower, right? Now all these points are valid, right? All of these points are valid. Yeah? All of them are valid. See, right here it's on the constraint, and right here it's moving again. We want to find the value that minimizes essentially what this circle is. Okay, we want the value that essentially makes this circle so small. Okay, because we're minimizing the value of the entire circle. I mean, I assume you guys know that the function described in this question is essentially just a circle. I'm just assuming prior knowledge there. But you've got that sort of regression inwards here, and when we hit 0, the size of the circle is minimized because there's nothing. But if you move further down, the circle starts to grow again, right? There's still going to be a big circle as long as you move down, even though the value itself is getting small. Okay, we're minimizing the function, and the function itself would be growing with negative values. So staying at 0 is our best bet. Okay. Now, if I instead change the constraint to 2, you can see here, and let me just change the slider just to show what I mean. Okay. To minimize the function here, okay, you can see that it can only really get bigger as we move on. So we want to essentially hit the smallest point that is still valid for the function to satisfy the constraint, which is right on the line. Okay, you can see that the central value of the function actually lies outside the constraint in this case, which is different to our previous example. But in this case, you can see that its best value is when it's just touching it, and anything further down is just going to make the function bigger. So we want to just keep it just at that constraint. So there's a difference here. Okay, so that's why we say for the best value in 2, we're going to essentially say that the best value is lambda equals negative 2/5. Therefore, the minimizing value is going to be putting 2 fifths into our function, negative 2 fifths into our function, but it doesn't really matter anyways. And you get a value of a fifth, which is our minimizing value. Okay, so actually to make it a little clearer, the minimizing value is 0 in the first one and a fifth in the second, because that's the minimum you can get. Let me just check I'm actually doing these correctly. Yeah, you've minimized it essentially. So you've got the 2 values that you've got there, which is, well, it's just 1, 1 for the first one, because that's at the point where it's just 0. And then for the second one, you've got this point here, which I believe is, 0.6, 0.8. So there's that. I should probably write that down as well. Okay, I think that's everything. Yeah. Okay, as usual, my notes are in the description. Ooh. No. To be honest, I'm quite tired. My desk right now is not so great. I've got a cut-off bag of biscuits here, a pot of watercolor paints that I need to wash out, and a pair of Teflon-coated scissors. How lovely. Okay, I think that's enough rambling from me. Have a nice morning, afternoon, evening. Hope you do all right. And yeah, guess I'll see you around. Bye.